Do you know why electrical engineering is so freaking hard? Because from our point of view, it doesn't exist. Modeling a mechanism is tricky, but you can feel when the parts don't fit. I wouldn't call myself much of a chemist, but I can still see and smell chemicals. But circuits? Unless you are currently watching it catch fire, you can't even tell if a circuit is on. Without the right equipment and the skills to use them, you're flying worse than blind. You're building entire projects on sheer guesswork. Today, we make the imperceptible tangible, and these inscrutable interfaces, we're gonna screw the shit out of them. Welcome to possibly the only piece of actual education at Voidstar Lab. Ladies, gentlemen, and cyborgs, I have a confession to make. Do you remember the $18,000 pro gaming oscilloscope from that time I built an $18,000 pro gaming oscilloscope? If not, welcome to my channel. I hope you like alliteration. Since the Pimpscope MLG4 2069 was forced onto an unwilling world, I've redone the tubing in hardline, I've added even more ergobleds, and I filled it with coolant that does not look like orange juice. It looks like something you'd dissolve a body in. But between you and I, and 449,000 other subscribers, I am afraid to use it. Even without all this extra. Oscilloscopes are just terrifying. They got buttons and dials, and what the hell does the squiggle even mean? I don't know about you, but I feel stupid just looking at them. Last year, this came to a head when I had to pull some unexpectedly intense reverse engineering to finish my new heads-up display. I was backed into a corner, and the only way out was to learn how to use my own stuff. I hate learning, but the hack that makes the Optagon work turned out to be so stupid. If I had just known how to use my tools properly, I could have crushed the entire project in a weekend. If I were a real electrical engineer, this is where I tell you to suck it up and go to school, because if I suffered through it, so should you. But I'm a business major with a YouTube channel. You got a circuit's got a problem, and to fix it right, we're gonna put those angry pixies under surveillance. I'm gonna tell you what you need, how to use it, and what to watch out for. Right after I thank today's sponsor. This crash course is brought to you by Keysight, makers of the most trusted test equipment in America, at least the pieces I didn't get my hands on. We're setting the stage for Keysight World Innovate, their 3-day virtual conference kicking off June 20th, 2023. Humanity is at a pivotal point. We have infinite knowledge in our pockets, we've never been more connected to each other, and I guess we have TikTok. Only the hardest problems remain, and the stakes of this game have never been higher. That's what Keysight World Innovate is all about, bridging the gaps in our technical legacy, protecting our planet and ourselves, and presumably making dump trucks of money along the way. Here's the agenda. Day 1, a deep dive into the 6th-gen networks that may finally fuse the virtual and the real. Day 2, the state-of-the-art in auto racing and how in getting an edge on the track, we're yielding a safer trip on the street. Day 3, the literal bleeding edge, AI-assisted healthcare that's always on call, and non-terrestrial networks that will wire up the final frontier. Join for free June 20th through 22nd, 2023 at the link in the description, unless you're already in the future, in which case you can watch the replays on your augmented reality implants that your AI surgeon installed during your self-driving commute. It's only 2 hours a day, and it's produced way more professionally than this bullshit. With the bills paid, let's boot this bad boy and break down the battlefield. Different tools are better or worse for performing different tasks with different signals. For instance, if you just want to make sure your 5-volt rail is actually 5 volts, a multimeter is going to get the job done in like 10 seconds. If your widget is browning out, you're going to have a hard time fixing anything until you hook up an oscilloscope and see what's actually happening. A logic analyzer can reveal what a sensor is saying to the microcontroller, and a debugger lets you see what your microcontroller's code is actually doing with that. If you can use each tool quickly and with confidence, you'll be able to spend more time fixing problems and less time guessing what they are from the symptoms. Here's my personal arsenal: multimeters, oscilloscope, logic analyzer, and specialized interface tools. Let's start in the simplest tool that everyone should have: the multimeter. The multimeter measures voltage, current, resistance, sometimes capacitance, inductance, forward voltage, and more. It's multiple meters in one. I'm only going to talk about voltage and current because we're dealing with the behavior of live circuits. The rest of those things only work when the circuit is off, ideally when the component is isolated. I actually use 2 meters as my daily drivers. The Fluke 87 is clunky but full-featured, and the Miniware DT71 smart tweezers are easy to grab to take a quick measurement. The big boy is the kind you want first, and I'm fairly sure this particular one is as old as I am. This is a very easy tool to use. Just turn the dial and get to probing. In voltmeter mode, it measures the difference in voltage between the 2 leads. The multimeter is a blunt instrument. All it does is take a bunch of readings, average them together, put it on the display, and repeat. I recommend buying a set of back probes. These come to a needle point that can bullseye those tiny little surface mount pins without shorting out the neighbors. The voltmeter's primary job is sanity checks. Is the power rail actually powered powered up? Is the reset button still working? Is the motor driver feedback at a sensible level? When a light isn't lighting, a beeper isn't beeping, or a battery isn't battering, the voltmeter will immediately narrow down where the issue is happening. If you connect the meter and the reading drops, you might, for instance, be missing a pull-up resistor, or maybe you just have a lot of internalized negativity. Most meters have separate modes for measuring alternating and direct current. If it doesn't seem to be working, make sure your probes and dial are set correctly. Remember to RTFM that manual. The AC voltage reading is often a root mean square estimate, which is more useful than a true reading, but it's a bit misleading. The peak voltage is actually about 40% higher. I'm going to say this a lot, but hooking anything up to the electrical mains is super dangerous, and for hobby projects, it is not worth it. Then I'll lose a subscriber. In ammeter or current mode, the meter measures current in amps. This is a bit trickier. You have to break the circuit and splice the meter into it. Remember, voltage is the difference between 2 points, but current passes through 1 point. An ammeter works by inserting a very low value resistor into the circuit, so you have to select the right range, often by hand, to get that correct resistor in play so it doesn't interfere with the circuit. Note that very few meters will measure below the milliamps, and even they're not that accurate. If you build a lot of battery-powered low-power gizmos, I would recommend getting an amplified interface to read microamp currents, like the microcurrent. As for figuring out where to start, just guess and check. You're not going to damage anything. I'll tell you how you will break stuff. You forget to put the meter back into voltage mode. Never leave a meter in current mode when you're done for the day, because current mode is basically a dead short. If you try to measure a voltage while in ammeter mode, something is going to go kablooey. Hopefully it's just a fuse inside the meter, and you're not turning a LiPo into a dynamite stick. If you're measuring AC current, alternating current, especially at higher voltages, you can use a current clamp. This clips around a wire and measures the changing magnetic field caused by the current flowing through the wire. The upsides are you don't have to cut the circuit or even shut it off, and since the current isn't passing through the meter, it's way safer. Downside, it can only measure alternating current since the sensor is a transformer. Also, you have to isolate the target wire. If more than one conductor is passing through the clamp, the measurement is useless. These are more useful for electrical than electronic work, and it's often cheaper to just buy a standalone clamp meter than add-on probes for your existing meter. Speaking of high voltages, that is dangerous. Attach the meter with alligator clips before you turn on the power, and never ever work on high voltage by yourself. Most meters just show the last reading, but some have a few useful bonus modes. If you're looking for a sudden drop or a spike, switch on minimum or maximum mode and listen for the beep. These are also useful for capturing a single reading when you have to keep your eyes on, say, the extremely dangerous 120 volts you're probing for some reason. A multimeter is really slow. If the glitch happens too fast, the meter will just miss it. Finally, some meters have a frequency mode and a duty cycle mode, which are useful for stuff like servo motors and sensors that use pulse trains or PWM. This is as good a time as any to remind you about the New Makers Welcome channel on our Discord. On there and on our electronics channel, we got hundreds of volunteer electronics helpers who are super nice, and they would love to get you unstuck. It makes them feel smart. Head to discord.gg/voidstarlab and tell them I sent you. I'll probably be there, so I'll already know. Anyways, let's talk about how a multimeter kind of sucks. As razor sharp as the probes are, and as easy as it is for somebody who isn't me to stab themselves with them like all the time, the multimeter is by design a blunt instrument. It can't measure fast changes, it isn't precise, and it doesn't have any memory, which is not helpful for problems that play out in nanoseconds. If the meter doesn't help right away, don't waste time on it. Escalate the situation to the oscilloscope. The Oscilloscope has a lot of mystique behind it and a lot of stuff going on in front of it, but it's actually a deceptively simple tool. An oscilloscope is really just a very fast voltmeter hooked up to a data logger, and all these buttons, dials, readouts, grids, lights, and menus just control how those data are visualized. I'm only going to be talking about digital sampling oscilloscopes today, DSO. Analog scopes use cathode ray tubes, and they have been thoroughly obsolete for 20 years, fight me. Millions, perhaps billions of times a second, DSO measures the voltage between the probe's tip and its ground, buffers it in memory, and upon a certain condition, plots what it got on screen. If I slow down the sample rate, you can see the confusing curve is actually just a time series graph with hundreds of milliseconds on the x-axis and volts on the y-axis. But milliseconds since when? Well, that's what makes this an oscilloscope. See, the scope isn't just recording the readings, it's looking at them, and when the voltage rises above a certain threshold, it triggers. The machine takes a few more readings, it displays what it has, and then it goes back to recording until the voltage falls below and once more rises above the trigger. Each frame of video is one complete cycle of a pulse or oscillation. So the oscilloscope is really showing you two things: how the voltage changes over a very short period of time and how that pattern changes from cycle to cycle. If you put the probe on a non-repeating signal, you'll just see noise. I'll show you what to do about this in a sec. So if you think about it, there are only three parameters to tune: how many readings to show at once, how much to scale each reading on screen, and what voltage should trigger that redraw. Most settings have a coarse and fine adjustment mode, which you can switch by simply clicking the knob. If your signal is consistent, you can even have the scope do this all for you. Just hit auto range and it'll tune itself to fit the whole curve on screen. Just don't trust anything automatic too much. If the signal is erratic or if it's pure noise, it'll still auto range itself just against interference, usually 50 or 60 hertz hum coming from the walls. The wires in the walls, not the walls themselves. This is a 60 hertz ghost! The primary setting for the X dimension is samples per division, in other words, how much time each grid square represents. You want to adjust this so whatever you're looking for fills the screen. You might want to see the whole curve, zoom in on a particular part, or back out to watch the greater pattern. The setting for the Y dimension is volts per division. Adjust this so your signal fills the screen. Don't rely on the grid lines for measurement, they're really just for reference. If you need exact numbers, switch on an analysis or invoke the cursor. These generally both have specific buttons on the front panel to bring them up. You should always use a 10x probe, so the reading on screen is going to be 1/10 of the actual voltage. Modern scopes can automatically compensate for this, though very few of them can detect it. So remember to manually switch the 10x mode on in both the probe and the scope. Note how the y-axis goes negative. You're probably building digital electronics, so your signals will bottom out at 0 volts. Don't let half your screen go to waste. This knob adjusts the offset to add or subtract a fixed voltage from each reading. You can shift it all the way down, then increase the scale to see more detail. If you ever lose track of where your curve went, just click the offset knob to reset it to 0. Some scopes also let you put a channel into AC coupled mode. This inserts a capacitor in series with the probe, so the signal is always centered around 0 volts. The x-axis counterpart is phase, or how far to the left or right the signal is shifted. This is a bit more complex than it looks. See, by default, the y-axis also goes negative. T-0 is at the center of the screen. The scope is displaying an equal amount of time immediately before and immediately after the trigger. Adjusting the phase forward drags the curve to the right, telling the scope to gather fewer readings following the trigger to display more of what led up to it. When you pull the phase backwards, that is, pull the curve left, you're telling the scope to discard more old readings to show you more new ones. It's not visually shifting it left and right, it's actually affecting what data is discarded and what is... I wrote is, but we all know data is plural. Don't lose track of the real world action the curve represents. If you're trying to see what happens when you switch on a gizmo, you want the phase shifted all the way back because, of course, nothing happens when it's off. But if you're diagnosing a brownout, you might want the reverse. You might want to see only what happened leading up to the trigger because you know what happens afterwards. The standard trigger is a rising edge. It fires when the voltage passes from below a certain point to above it. This isn't always what you want, so there are a few alternate triggers. You can fire on the falling edge, you can fire on either edge, you can fire based on a pulse, that is when the signal spikes or cuts out for a certain period of time. You might even want to read one signal in response to a second signal, like capturing data after a hardware interrupt. Some scopes have special triggers for stuff like analog video, line audio, or even protocol triggers that wait for specific data. You'll know if you need these, but you probably don't. The default continuous mode clears the screen after a short timeout. So what happens if the signal you're trying to probe doesn't repeat, like you only see it for a split second and it vanishes forever? That's what this guy is for. When in one-shot mode, after the scope triggers, it will pause instead of beginning to record the next cycle. Once you press this button, it'll stay armed forever, so this is how you can catch rare random phenomena that take hours to show up. While the scope is paused, you can still adjust scales and offsets, but remember, you're just zooming in on whatever you captured in the first place, so the resolution is getting lower and lower. I'm gonna be honest though, the main use of one-shot mode is freezing the screen so you don't have to keep holding the probe. Keeping the pointy end in the danger zone and the ground connection, like connected to ground, are like the hardest parts of using the Oscilloscope. You have two options for grounding, the alligator clip and the pin. You can clip the clip onto stuff like metal shrouds, mounting screws if there's a chassis ground, or a through-hole wire. In a pinch, you can just scrape some solder mask off a ground plane near the edge of the board and just bite right onto the side. Professional development boards will often have these little wire loops specifically for alligator ground clips. They're gator aids. The ground pin slips over the tip of the probe and it's much shorter, so it's better for stuff like high-speed transmissions, feedback lines, and just any place there's no convenient gator parking. To use this thing, wedge the tine against a nearby component's ground pin and use spring tension to hold it in place as you move the probe onto the signal. If you're lucky enough to have a wire lead or header on the target line, you can snap on the grabber hook and just latch this thing in place. Otherwise, you're going to have to hold the probe in the danger zone while you perform tests, adjust settings, and take notes. You are taking notes as you measure, right? Like, do you really trust that you can remember all of your findings and all of what led up to them? While you're scribbling, don't let that business end slip. It's going to short everything out. This is one of those times you really want a lab partner because no clamp, helping hand, or flexi arm seems capable of keeping a scope probe put. If you're a lonely sad sack, a company called Keysight makes these special gooseneck probes. If you're lonely and cheap, you can try to solder a wire loop onto the target pin or trace to give yourself something to grab onto. Just remember to tape all this down or you're 100% guaranteed gonna rip that probe and the trace right off the board. So you got some waveforms. Now what? Let's see some common patterns to look out for. See how the signal is overshooting then wobbling a bit as it settles? This is parasitic inductance. This circuit might need a termination resistor, a decoupling cap, or simply a shorter trace. If this gets really bad, this voltage spike can actually start blowing out components, so you might even need like a TVS diode. This is what the opposite looks like. The slow rounded rise could mean a signal's impedance is too high, pull-up is too strong, or a capacitor is too plump. Just a heads up, both spiky and round corners can be caused by the probe. I'm going to explain how to fix this in a second. Here's an interesting one. I have put the probe on a chip's VCC pin in AC coupled mode. This should be a steady straight line at 0 volts because our 5-volt rail should always be 5 volts. But it's wiggling. This is a sign of voltage dropout. This component needs more decoupling caps. Let's enter the time domain with a signal that's jittering around left and right because the Atmega's onboard timer actually kind of sucks. Here's a curve you definitely want to get to know, the test output on the scope itself. This is that little metal loop and it usually emits a nearly perfect 1 kilohertz square wave, generally plus minus 1 volt, and it's on at all times. If the corners are rounded or spiky, you have to adjust your probe's serious phases, shunt capacitance. Just check the side of the probe for that little recessed screw and turn it till the square wave is squared up. If your square wave already looks good, make sure your probe is in 10x mode, which it should always be. Final tip. You can measure current with an oscilloscope. Measure a milliohm resistor with a precise multimeter, jot down its actual value, break the circuit, solder the resistor in series, and measure the voltage drop across it. Then you can use Ohm's law, or better yet, your scope's math mode to calculate the current. I'm aware you probably have a different scope than me. In fact, I hope you have a different scope than me. But I want to emphasize, no matter what you got, the control panels and readouts are basically standardized across all oscilloscopes. Models start differing in the specs and the special features, stuff like Fourier analysis. This transforms a signal into a set of overlapping sine waves, which reveals telltale signs of certain analog shenanigans. Shenanalogs, analanigans, I'll workshop it. The specifics are beyond the video and frankly the video creator, but if you build analog stuff, I've been told the frequency domain fucks. Scopes can get kind of expensive, like, you know, not necessarily $18,000, but a decent new prosumer model can cost $500 or more. The good news is that circuits haven't really changed in like 50 years, so cheap used scopes are everywhere. Just remember, buy digital, check reviews to make sure the interface is easy to use, and remember to make sure it's got at least 4 times the bandwidth of the fastest signal you're likely to encounter. 100 megahertz is a good amount. Some scopes allegedly artificially lock out features so the manufacturer can sell the same product at different price points. And I've heard that certain models can be jailbroken into a higher end version. One of these features is highly useful but not necessarily worth paying for. This is a protocol sniffer or decoder, which takes a digital data signal and translates it into human-readable text. This doesn't really play to the oscilloscope's strength. Transmissions are much longer than a single pulse, and there is usually a long downtime between them. So if your scope doesn't have a logging feature, it might not have enough memory to even grab the whole message. Still, this is a very important tool, important enough to deserve a dedicated piece of hardware. If your projects use microcontrollers and embedded computers, which in 2023 they pretty much all should, you owe yourself a logic analyzer. A logic analyzer is sort of like a stripped-down oscilloscope with only a single bit of resolution. It's all you need. Digital signals are either off or on. In return, you get more channels. Even an entry-level logic analyzer can capture 8 lines at once, which is more than I've ever needed. The logic analyzer is a tool that you'll want to keep connected throughout the whole programming, troubleshooting, firmware development process. This is a tool specifically designed to eavesdrop on chip-to-chip communications. If you're just making basic hobby projects, you can get away with a usable logic analyzer for as little as $20, but a quality workhorse will cost $300 to $500, and if you build a lot of electronics projects, it's usually worth it. The Benjamins are letting you watch your chip-to-chip chatter as it happens and record as long as you like. Past this point, the returns are very quickly diminishing. Like Keysight, for instance, has far more advanced units with super advanced front ends that can analyze much speedier signals like USB and video interfaces. Unless you're developing a product, you will never ever need anything even remotely close to this. All logic analyzers have built-in protocol sniffers, and the nicest ones will even figure out what they're looking at automatically. These are great for spotting low-level trouble like failed checksums, confirming your 400 kilohertz I2C is actually 400 kilohertz, and verifying what a device is sending and receiving is actually what you expect it to send and receive. You'd be surprised, even if you wrote it yourself. If you have spare lines, it's always a good idea to hook these up to things like debug consoles, interrupt pins, because you don't always know what you're going to find, and that extra context can really make a difference in helping you debug it. The logic analyzer is the primary tool for reverse engineering. It's your best way to find an entry point. It lets you capture known working commands to replay later. Some components like FPGAs actually store their firmware on a separate chip. So if you can intercept that traffic, you can hoover up the entire code base. If you correlate traffic with console output, you can also reveal how the bootloader is configured. Occasionally, the target itself will basically show you the entry point to the code it's bootstrapping. It literally shows you how to hack it. Speaking of fast, we got USB, Ethernet, PCI, and the low voltage differential signaling used in liquid crystal LCD displays. These aren't just ridiculously high frequency, they encode data in differential pairs. These require much higher end equipment to sniff. Then you have HDMI, DSI, CSI, and DisplayPort. Even if you could keep up with them, the protocols are proprietary, so odds are you can't even do anything with them. If you do find yourself probing any of these signals, you are in way too deep. This is one of those times you're going to want to modify an off-the-shelf product. You do not have to develop everything yourself. You have to finish the project. But sometimes the information you need is inside a chip. That's when you need a debugger. You may have used a JTAG or SWD adapter to unbrick a microcontroller or burn some flash memory, but it's also the ultimate debugging tool from any kind of microcontroller. I mean, any modern microcontroller. I'm looking at you at Mega328. If you're brave enough to leave Arduino for Visual Studio or another professional IDE, a debugger lets you pause the code, read anything in memory, step through your firmware line by line, and when something goes wrong, you get exhaustively detailed crash dumps. Embedded toolchains are notoriously hard to set up, but it is infinitely more productive than putting in serial prints every other line. This is an action I can call you to. Would you like a dedicated video about how to use fancy pants debugging? This is another one of those topics that's super useful but way too confusing for absolutely no reason and doesn't require me to build a project. Let me know in the comments, and while you're down there, hit subscribe. Worst case scenario, you watch another one of my videos. Just do your homework. Certain manufacturers, STM, try to lock you into their proprietary Xilinx debuggers. Freescale. Man, my anti-consumer hay fever is really bad this season. Our final category is wireless. You can't have electricity without the magnetism. I'm gonna be honest, radio is where my expertise completely falls off a cliff. It's extremely technical, and it dips real hard into the real electrical engineering that I would have learned in college if I weren't a zero-discipline shithead. You can go your entire hobbyist career without ever dipping into low-level wireless. In fact, I recommend doing so, but for completeness, I'll give you the Colorado 1-mile view. Earlier I talked about the spectrum analyzer. This is the oscilloscope of the airwaves, and they're among the most expensive and complicated pieces of test equipment. You can get less expensive spectrum analyzers like the RF Explorer or the Red Patea. If you have a few bucks to throw around, you could also grab an RTL SDR. These are software-defined radios. They use a combination of funky hardware and pure black magic to tune into specific frequencies within a hardware-dependent bandwidth. Actually, I think most of them use Fourier transforms, he said callbackingly. You can use these things to sniff wireless traffic, intercept video transmissions, tune into radio, find Wi-Fi dead zones, among many other things I don't know how to do and have never had a need for. Low-level RF is something no hobbyist should ever get themselves tangled up in. Life is too short to roll your own radio. You could be having sex, or you're asexual, and you could be not having sex. You people who do things just to learn are f***ing psychotic. And that is my crash course on the test equipment you'll need to make the electrical palpable. If you take anything away from this video, please make it this. As early as possible, get yourself quality tools and use them constantly. Build these habits and muscle memory as early as possible. There are just so many ways for hardware to go fucky-wucky, and until you start looking at some waveforms, you are only guessing at the cause. The DC offset carrying Voidstar Labs alternating current is our patrons, like lab scientist KRZ0001, Virtual Raj, and Polarized Ions. Our venerable collaborators are What the Chuck, Moonkin, Keep to Yourself, Caster the Catboy, Dysfunctional Potato, The Benevolent Misanthrope, The Suits Ruined Our Fun, SXP, Bitrot, Schleppy the Schwagster, E to the iPie, Turner Zay, and I'm literally only paying this so some dumb kid might get interested in STEM. I have made them permanent parts of my workshop and hidden their names throughout this episode. It's probably going to confuse the hell out of anyone actually trying to learn, but that's what you get for trying to learn. If I had a nickel for every one of our silly named lab assistant supporters, they would be cheapskates. Thank you, Dempsers, Ashley Coleman, N8 Protagonist, Socks McGox, One Handful of Beans, Ryan Gooler, Mayhem Nasal Spray, Microwave, The Antiva, Juicy Legend, Drinker of Juicy Legendary Fruits, Jason. I'm working on every resin video and it'll be out next week, I promise. Yo, send me the link, I want to see that. The Monk, Vorka, Azunda Wielder of Iron, Heater of Shrink, Storm Bee Design, Kermit the OG Frog, Callsign Carrot, Jamie, Apona Tratza, Pussy Nugget, Eddie, Oritnus Nair, Brad Cox, Quality Doggo, Cindy Lauman. But seriously, ladies, gentlemen, Cyborgs, every name I just read out loud is fake. Seriously, on with the real subscribers. Onyx Plague, One Sleeve, Elite Giant, numbers, HJ's for the hobos, John Loves Jen, Karinamon, not a Digimon, Zapf, Incognito, Cameron Ogletree, Nathan Johnson, Matthew Arrington, Max Luck says, you're too hard on yourself, love yourself, idiot. I don't know why I decided to read that in an Arnold voice. Steven, 6 foot, 6 figures, 6-pack Schulte, Sunburnt Cat, Doom Crew Inc., General Buck Turgerson, Zash, Bob Dobbington, Entropy isn't what it used to be, Powerful CCH, Good Lady Nat, Queen of Lemons, Victor of the Great Citrus Wars, Period Clots, Cullen J. Webb says, Isis J. Osway, Ommunist K. He didn't speak Pig Latin, though, he spoke Pig Aramaic. Visit OmahaThreeDprints.com for all your 3D printed RPG product needs. Bryn Wolf Schulte, not Brian, I am so sorry. Bill Schooler, Reagan says, save the bees. My husband watches this shirt, so hi, Urch. Anthony Evans, Rusty Flute, I inspired the Next Layers YouTube channel, so you guys should check it out. Amanishi, Sharia Coleslaw, Cats, Eval Bunny, Dax Dashly, Seek Seth Checks, Lydia K, Cody, Michael Roche, Boulder Creek Air, James, Craft Computing, Granville Schmidt, Trans Rights. That's relevant for this month. Sticks, like the river, not the band. Brian Cofford, Bob Forbes, Max Steel doesn't have the balls to play Extraction. A. Big Bob's Gaming, Travis Hippa, The Cuttlefish, Jan Pavo 2137, Nova Ren, Bump Tickley 69, Quantumly Tangled, Roger Pinkham of the Great Star Theater, Burn Duck 3, Kink Shaming Walrus. It shames, and it's got tusks. DBD, Topher, Blammo, Big Bird Tommy, What Goes Bump in the Night, K Panic, Measure Twice, Measure Once, Cut Twice, Reglue, Cut Again,
Iron Rain.
Cliff Henning, 6A, 6F, 65, 6E75. Jason Terrian, in bed. 603, Talon Democratic Socialist, and Pretty Righteous Dude Dash Zack. Acorn, RJ Dipcord, Xanthorian. Mike Kelly, Thunder Chicken. Michael, Rinry, The Lizards Are Watching Zack. Sir Jack Cooper, The Second Wilder Frying Pan. Cross-threading is just free Loctite. Dr. Mrs. the Meerman, 3,735,928,559. Adam Birch, Micah, I'm still sitting on a first edition morphing jar of Freedman. Cacophony of Failure, My Dog is a Bear. Travis, why did I say Travis? There's no Travis on the screen at all. Dennis Kempen, VK2KTJ, Kevin DeGraff, Skirto Saggins, Burn It. Danny Devoid of Life, Trump did nothing wrong, Good Suck. Vajelli, Aaron Steers, John Marler, Bootsy von Poopstein, Sebastian Safari, SKL Scratchfinger, Carlos Dubin, Circle Zero, Samuel Roosh, 1.05 times 10 to the 62nd, Jessica Mauerhan, and Tegan. Man, I could really go for a juicy legendary fruit RN, no cap, yeet! Thanks for watching, and I'll see you above a certain voltage threshold in the future.